will start with Fibonacci heaps. I will do the remaining part of Fibonacci heaps. So remember we had this binomial heaps where we could do a bunch of operations. We could do heap one time again all order one delete min is order log n, and meld combining two heaps is in order 1 for lazy and log n for the other one, correct? So these are the operations we have seen, and now some more operations, decrement, and which we want to do again in order one time, and delete min. No, delete min, delete, sorry, just delete. Again, we want to do this in order log n time, correct? We want to delete some element, correct? So how do we do this? So the point is we could do so decrement is not very hard. When you decrement, if the decrement, what do you call it, in heap H, the item I, you decrement it by delta item, and this is the decrement value, decrease value by delta, correct? And this is the heap, correct? So if this disturbs the heap property, maybe delta is small and you decrement and nothing bad happens, its parent is still smaller, then there is no problem. Otherwise, you so if decrement does not harm the heap property, all is well. Else, you cut at I and meld, correct? So you meld it in the heap. Similarly, in delete, you so you cut at I, change value of change value by data and meld, correct? Meld all the children and so on, correct? So meld along with children. Do you follow me?
Yes, sir.
So along with children, what do I mean? No, I do not mean this. I mean that you just meld. So when you decrease the value will still be smaller than all its children. It might become smaller than its parent. That is the problem. So you cut I, update by delta, and then meld the subtree rooted at I with the heap edge, correct? In delete I, you just remove. So you cut I, form heap of children of I, and then you meld heap H prime of children of I, meld H prime with H. Correct? Now you might say that, oh, okay, we are done. But the problem is the tree might get shallower and shallower. So you cannot guarantee that it is of depth. Its depth is logarithmic in the number of nodes contained in it. So you cannot arbitrarily keep on clipping branches from the tree and making this work. Correct? Somehow you have to reconstitute the tree. Correct? Are you with me? So how do we ensure that the size of the tree is at least, we want to guarantee that size of tree is greater than 2 to the depth of tree. Correct? 2 to the omega of depth of tree. Correct? Some c times depth of tree. Correct? And how do we ensure that? So we ensure that by ensuring that we do not allow the trees to grow. We do not allow arbitrarily many cuts inside the tree, inside a subtree. Correct? So what we do is we do not ensure that a tree loses at most one child. Correct? If it loses the second child, you just remove the, you cut it out from its parent and meld it with the rest of the graph. Correct? With the top heap. Correct? So arbitrary cuts inside the tree are not allowed. Correct? This might lead to cascading cuts. So so let me get to it in 1 minute. So suppose you have a tree, and this is I somewhere. You say you want to delete this I, so delete this I. This tree now you would take its children and form a new heap from them. So this would go to this with a something like this here, and this part goes to a new heap. Correct? So the suppose the children were some number of children, there were some number of children, and now this is the new heap H prime, and you meld H and H prime. Correct? So in this process, this scarring might lead to that. This might lead to multiple scars. Correct? Which means the tree might become very shallow. And to prevent that, what we do is that a node can lose one child, of course. So suppose you have a node which is, let's call it X is any vertex, and suppose it has children y1 through ym, correct? And it loses, so it has children, and in particular yi is a child, the ith child, where we numbered the children according to the order in which they were added to, they were in the order in which they were linked. So y1 to ym are in the order they were linked with X. Correct? Remember that the invariant was you can link a vertex x to, so you can link y to x, link a y with x only if rank of y equal to number of children of y equal to rank of x. Correct? So I'm just recalling this invariant. This is the same as in binomial heaps. You can only link things with the same rank to each other. Correct? So consider a child yi when it was linked with x. Okay? At that point of time, x had at least I children, I minus 1 children. Correct? So it had children which were at least y1 through yi minus 1, and maybe one of the child has been cut in between. You cannot be, so the second invariant that we have is that you cannot cut more than one child of a vertex without cutting the vertex itself. Correct? So if you cut the second child of a node, then you also cut that vertex and put it in a new heap and along with its children, and then meld the thing. Correct? So this is the second invariant. Okay. So now when yi was cut, when yi was, so no, not yi was added, was linked with x, it had at least, x had at least I minus 1 children, because there namely y1 through yi minus 1 plus another y possibly somewhere, one of the y's somewhere. This y could be anywhere. Correct? Are you with me? So rank x must have been at least I minus 1 when yi was linked. Correct? With x. Now, therefore, this means that rank of yi was greater than equal to I minus 1 when yi was linked with x, because its rank is equal to the rank of x when they are linked. Correct? After that, yi might have lost at most one child. So yi can lose at most one child subsequently without being cut off from x. Correct? Which means rank of y is greater than I minus 2 currently. Correct? So this is what we wanted to prove, that the ith child of any node has rank at least I minus 2. The ith child has rank at least I minus 2. Correct? Are you with me?
Yes, sir.
Okay. And now how is this useful? I would like to claim that this alone tells us that the tree has at least the tree. So one second. So what I would like to claim is, if rank of R is greater than is equal to I, then size of R is at least the Fibonacci number I of I. How do we prove this? Let's do this. Let's prove this by induction. So let's create the smallest node with rank 0, 1, 2, 3, so on. I will not complete the proof, but I will give you sufficient hints so that you can complete the proof. So first, let us look at rank R equal to 0. So what is the tree? It must contain a single node. Rank R is equal to 1. It must contain so how do we prove this? Rank of, if it has one child, can it have two children first of all? Rank of R is 1, so it has one child, correct? So it cannot have two children. Now this, okay, so this invariant tells us that rank of y1 is greater than -1, which is fine. So okay. Okay, now so after the trivial cases, let's come to rank 2. So it has two children, of which the second child, let's call them y1 and y2, rank of y2 is greater than equal to 1, greater than equal to 0, correct? So the largest tree must contain just this. Now what about rank R is equal to 3? You would get 3 children, and the third child is exactly equal to this. Why? This is y1, y2, y3. This must be y3's node must be rank 1. So it must be like this. Correct? Rank R is equal to 4. You would get 4 children. And the third one must be like this. And the fourth one must be like this, namely this. And now you can see the pattern that you are taking the so recall, just notice that this is this tree and this is this tree. Here this is this tree and this is this tree, and so on. Correct? So what is the next in the sequence? Rank R equal to 5. You take this tree, this entire tree, and attach the previous tree to it. Correct? So this leads us to conjecture that if ni is the number of nodes here, ni is equal to ni minus 1 plus ni minus 2. And the base cases match with those of the Fibonacci sequence. So indeed, we get the Fibonacci sequence. Correct? Do you agree that ni is equal to fi? Because the base cases also match. N0 is equal to 1 and N0 equal to 1 and N1 is equal to 2. Correct? So starting with those, you get the thing. And now we know that therefore ni is greater than equal to some phi to the power I or something like that. Correct? Which again you can prove by induction, where phi is root 5 minus 1 by 2, the Coulomb ratio. Correct? So we have shown that these they not not shallow. I mean, not shallow meaning they are not sparse. Correct? They have exponential in the number of children many nodes. Correct? So, are there questions here? Hi. Are people there?
Yes, sir. So when we are deleting an
Yeah.
element from binomial trees,
Huh.
is the result a binomial tree itself?
No, it's not a binomial tree.
So then, sir,
You
how do
cannot
we?
delete an element. You only delete the minimum element.
Okay.
So when you delete a minimal element of a binomial tree, you get only binomial trees, and then you combine them again, and this again becomes a binomial tree.
Okay, sir.
Correct? But in Fibonacci trees, you can delete at arbitrary places. That is the power that Fibonacci trees gives you over binomial trees. Correct? Correct?
Yes, sir.
Okay. So now, topic. So let's move on to another topic related to hashing. Correct? So what is hashing? Let me explain this via the dictionary problem. So what is dictionary problem? So firstly, this is a completely different topic altogether. Yeah. So you are given a set S of items. You want to look up the items based on key values, on a key value. Correct? So you want to, so in the dynamic setting, what is, so this is just what you have in a Python dictionary. So dynamic we want to support. One is insert. You want to put an item in the dictionary. You want to delete an item from the dictionary, and you want to look up the item in the dictionary. Correct? Am I clear? Yes, very clear. Okay. So now one way to do it is using arrays. Correct? You have, so some key suppose 80 80 characters long, and each char is 7 bits. Correct? Which means it can take 128 values. Correct? 2 to the 7 values. Then how many keys are possible? Anyone?
80 into 2 raised to 7.
Sorry?
80 into 2 raised to 7.
No, lot more than that. 2 raised to the 7 to the power 80.
Oh, yeah.
Correct? this is equal to 128 to the 80, which is a humongous number, correct? Equal to 2 to the power 560, correct? So this is a humongous number, much larger than the number of elementary particles in the universe. So you cannot hope to build an array of this size. You cannot say that I will build an array which has an array A, so that AK stores the value of item with key K. This is infeasible. Correct? So what you want to do is to hash the value of K. So you want a function h that converts K to some h of K. Correct? And now you want to store the value in A sub h of K. Correct? For example, you might choose this h of K to be much smaller. So firstly, and on what parameters would you choose this K? It would depend on the size of the set S. So for example, very trivial example, if you want to solve keep just 10 items in your dictionary, maybe, then you certainly do not need the values to be, the number of slots to be much larger than 10. You don't need millions and millions and millions of slots, correct? At least, is the intuition clear?
Sir, even if we don't store any value, do we need like 2 power 560 element spaces?
Even if we don't store any values, meaning?
So like, if the size of the set S is small, like we don't need,
Yes.
yeah, 2 power 560 elements.
Yeah, so the key is 560 bits long, but you don't need to create 2 to the 560 different possible slots, correct? You need maybe like 10 slots or 20 slots or whatever, correct?
Yes, sir.
In actuality, you would want just 10 slots, correct? 10 slots should be sufficient. But how would you search for them? So let me make this slightly more precise. So if you store key K, if you store the item with key K in AHK, and so now what could happen? That K1 and K2 both get mapped to the same slot, correct? So this is called so HK1 is equal to HK2, suppose. Then two things get mapped onto the same slot. Now there are many ways to deal with this. This is called a collision. When the hashed values of two keys collide, they map onto the same slot, correct? So one of the most popular ways of dealing with this is called separate chaining. And there are many disciplines like you can pick the next. So first let us look at separate chaining. So each A of H of K is a linked list, correct? So lookup is go to slot A of H of K and search sequentially for key K, correct? Okay, now insert is just append or prepend to slot HK, correct? And so let's say prepend, this takes order one time. You don't have to traverse the list. And delete, find the key K in list A HK and delete. I mean, there's just a linked list deletion, correct? So now you can see that insert is of course order one time, but these two take time proportional to the order of the maximum length of the list, correct? Correct? Which is depends on how many collisions you get. How many things have the same value? How many keys get hashed onto the same value? That is the length of the list, and your lookup and delete depends on those, correct? So what are the desirable properties that we have of hashing? By the way, can you hear me? The electricity is gone. Yes, I was just something went wrong. Hello?
Sir, your voice is breaking.
My voice is breaking. Am I clearer now? Am I clear now?
Yes, sir.
Can you hear? Okay. Okay. Because my Wi-Fi shows that all the rings, so it should be fine. Okay. So desirable properties are that there should be small number of collisions, and small table. We should not need to build a table which is millions and millions and millions of slots long, and H should be easy to compute, correct? So if you have the property 1, 2, and 3, 1 and 3 together constitute what is called perfect hashing, correct? In a quantifiable way, you want small number of collisions and it should be easy to compute, correct? But now notice, and the table is small, however small we can make the table to be. We cannot make it to be sublinear because you're storing n items, then you would require at least n space. So ideally this should be order, this should be order n, this should be order 1, and this should be this should be order 1, correct? So how do we ensure that? So first we will see the bad news. So what is the bad news? That if you fix a particular edge, then there are sets of n, or let's write capital N, of n items, okay? Said that for for a table of size M, at least, not at least, all n items get hashed onto a single slot. This assumes that the size of the universe is fairly large, or is not very small. It's so if u is greater than equal to n minus 1 into m plus 1, then you can do this. I mean, even for quadratic universes, what to say of humongous universes like 2 to the 560, even for quadratic universes, such a if you fix h, then there is a set, there is a set S of n items, so that all the n items get hashed into single slot. Now, can you tell me how to prove this? Just an existential proof. Tell me.
I think pigeonhole principle.
Yeah.
We will.
Tell me how.
Yeah, just a second. I need to work out the details.
Yeah. So basically, you just
Yeah.
take the.
Okay. Yeah. Should I say it, sir?
No, you tell me. Yeah.
Okay, sir. So if we have more than n minus 1 times m items in our universe, then assuming that, like in our worst case, this is saying it slightly loosely, but in our worst case, we will put we'll put n minus 1 items in each of the m slots, but then we still have something left over. And this is assuming we can only put n minus 1.
Yeah. So the average would be u upon m. So at least one of the, at least one slot gets ceiling of u by m many items, which is equal to n. Correct? So no, why does this work? Sorry, I'm confused. But anyway, it follows from the pigeonhole principle, correct? So I will let you think about it. Correct? So with this bad news, a single edge cannot work. But what does work is a random choice of edge. Correct? So if you set, if you choose a, so the answer to this, the resolution of this problem lies in saying that use randomization. So one edge does not work, but a family H is equal to H from U to 0 to m minus 1. This will work. And what is this family? We will see later. But there are many such families, but we say that a family is universal. So universal family of hash functions if for all xy belonging to U, x not equal to y, take two distinct elements from the universe, the probability over this h from h of hx equal to hy is less than equal to 1 by m. Correct? So we call this a universal hash family with the parameter n, correct? And now, so this is called a universal hash family. Now you can see that we can create you can create perfect hash tables using these hash families, correct? So how do we do that? So how do we create universal? So how do we create perfect? First, we will show how to create perfect hash tables. So perfect. What word did we call that? Where did it go? Yeah. So these something that satisfies small number of collisions and easy to compute. We can create those using hash tables using order n squared, where you take n squared sized tables, n squared of n squared size. So how do we do that? And then we will see how to reduce this to the optimal value order n, either today or next time. So most probably today. So how do we do that? Firstly, notice that if you fix x belonging to u, correct? What is the probability of so then collision probability with x is equal to how much? Tell me. Collision probability of one element of x and y is 1 by m, correct? Hx equal to hy is 1 by m. So if you hash all the elements of S using the hash function, then the probability that hx equal to hy is less than equal to 1 by m. So probability that there exists a y such that hx equal to hy is less than equal to, just by the union bound, is less than summation y belonging to S minus x of the probability that hx equal to hy. So here I should say x is not equal to y, x is not equal to y, correct? So this is less than equal to probability y belongs to S minus x of probability hx equal to hy is less than 1 by m. This should be equality, in fact, or is less than. Because we are using the union bound, and this is less than n minus 1 by n, which is less than n by n. Correct? Are you with me? Okay. So now probability there exists x, there exists y, hx equal to hy is less than equal to how much? Is less than, I claim you just go over all the n x's, and this is less than n squared by m. Correct? Are you with me?
Yes, sir.
Okay. So then this means that probability there exists collision is less than n squared by m. So if you take m is equal to 2n squared or something, then you get probability of collision is less than half. Correct? And now if you use Markov's inequality, you can get if you use Markov's inequality, then you can just take this to be slightly larger. If you take m is equal to 4n squared, then WHP there will be no collision. Correct? Correct. So basically you have to take it take the table to be quadratic. Correct. So quadratic, the message of this is that with quadratic tables, it's easy to prevent collisions or minimize collisions. Correct. Prevent collisions. Correct. The number of collisions is just 0. Correct, with a high probability. So now the question is this, but still the overhead on the tables is quite large. It is quadratic. So if we want to reduce this to a linear thing, then how do we do it? So any suggestions? How would you do it?
Sir, I had a clarification I want to ask. Sir, so the statement that we're making is that given our 4n squared hash functions, so we have 4n squared hash functions, and if you pick a random...
No. The table is of size 4n squared. The hash functions are from u to 0 to 2n or 4n squared or 2n squared is order n squared minus order n squared. This is equal to your n, correct? N minus 1, whatever.
Sorry, just a second, sir.
Sorry?
Could you repeat that one more time? Sorry.
So what I'm saying is you take your universe and map it onto m squared so the hash values are 2 log m bits long or order log m bits long. No, what am I saying? Order log n bits long. 2 log n bits long, correct? If you can create hash functions which are universal in the following sense and are of length 2 log n, the output is of order 2 log n length bits long, then we are done.
Oh, okay, sir. Okay. Thank you, sir.
If there's confusion, tell me.
I think there is still some confusion, but I think I might need to think about this and read it again. I think I get what we're doing on the big picture, but I think to get the details, I might need to go over it again.
Okay. So my point is just this, that you hash on this, the keys to a small range from 1 through n squared or 2n squared or something, correct? Then with high probability, there will be no collisions. How do you get this n squared? This we will see next time. There are many ways of doing that, of creating such hash families. But if I tell you that for every m, you can create a hash family of this form, which satisfies this property, this universality, then we are done. Correct?
Oh yeah, I think I see it now, sir. I think I got it. Yeah. Yeah.
Okay.
Thank you, sir. Yeah.
Okay. Okay. So, but given universal families, if you want to create linear size perfect hash functions, then how would you do that? Instead of quadratic size, you want to map it onto values from 0 to n minus 1 or 4n minus 1 or 100n minus 1. Correct? But not quadratic, just linear. So any suggestions how would you use this scheme to do this more general thing?
So could we replace 1 by m with 1 by m squared in our condition of universality?
Yes. So here we take m is equal to n squared. We choose a hash function such that m equal to n squared. But this will not, I mean, if you replace it by n, so we want basically a hashing scheme in which there are linearly many slots, correct? And they are used to store linearly many values, and yet there are no collisions, or with suddenly high probability there are no collisions. Is the question clear to everybody? Please interrupt me if the question is not clear. Forget about the answer. Just if the question is the question clear or not? So what we want to do is to have small number of collisions or zero collisions ideally, correct? So let's call this 0. And you want a small table of linear size, and H should be computable in order 1 time. Correct? So it should not be very complicated. For example, one way to do solve this problem is to keep what is called cuckoo hashing or something. You put it in the next empty thing, or you throw something out and put it. So there are more and more complicated ways of doing things. But what is the simplest way you can think of where the number of collisions is 0, the table is only linear, and H is easy to compute in order 1 time?
We just index, right?
Huh? We just
Index it, like we take the hash 1 by 1 and assign it 1, 2, 3.
Sorry, I didn't understand. Could you repeat that?
I mean, when we insert elements, we just sequentially output the hash.
So you are saying you hash with the first hash function and the second hash function and so on. Oh no, what are you saying?
Never.
Okay. So one very simple scheme to ensure this is to have a 2-level hashing. Okay. So suppose you build this table so that there are some n slots, and in the first one you get n1, n2, and so on, n many entries, correct? In the ith slot, you get ni many entries, correct? Okay, this is what is going to happen if you just blindly do this with you take m is equal to n, and then you build this table of size n, and you do this, then there'll be some collisions, correct? So there'll be some collision. Ni things will be sent to one slot, to the ith slot, correct? Are you with me? Now, how do you resolve this? So what you do is you build another table here of size ni squared correct, which enables you to in one lookup, it helps you. I mean, so to look up this thing, correct? So basically, I'm saying that you have a two-level hashing. The first hash function h0 takes you to one slot, and in that slot, you apply a hash function hi, which takes you to one of the ni squared slots. So if we can guarantee that summation ni squared is order n, then we are done. Correct? Do you agree with me? So what is the expected value of ni squared over the hash functions h naught? Tell me. If you take your m to be n, what is the expected value of ni squared? This is equal to so tell me, is equal to no, are you with me or no?
No, sir. Yeah, I did not understand this part.
Okay. Okay. Let me start again. So you take your m to be equal to n, correct? Previously, we were taking m is equal to n squared. Instead, you take m equal to n, correct?
Yes, sir.
So far, so good, correct? Now, when you build this table with m equal to n, and so there are n slots, correct? In the ith slot, you are bound to get some collisions, correct? Not too many, but some collisions. Let's say ni collisions. Ni things map onto the same slot, correct? Correct?
Okay, sir.
And there we were saying we would build a linked list. Now, instead of building a linked list, we built another table provision to handle these ni's, these things, ni items using ni squared many slots. Are you with me?
Yeah, this is where I did not understand, sir.
Okay, what is the problem?
So there are ni elements in the ith slot.
Huh. And you build a table.
Okay. So like in the previous case, we were building a table with ni square slots.
Yes.
Okay.
Correct. So if the expected number of ni squared is equal to order n, then we are done. Correct. Sorry, expected number of sum of ni squared is over all i's is equal to order n, then we are done.
Yes.
Correct. Now let us try to prove this. So how would we do that? So we have to calculate. So let ixy be the indicator variable if hx equal to hy, if there's a collision, and 0 otherwise. Correct. Just the standard indicator variable. Correct. Correct. And now let us look at this summation ixy over all the y's and over all the x's. Correct. So I am writing I h0. Let me put h0 here, h0 here, correct? Correct? So what is this equal to? I summed up over all x's and all y's, correct? This is equal to the sum over all x's of the sum over y, which is not equal to x. So here I should say belong to S, x belong to S, y is not, say that y belongs to S, ixy plus summation y equal to x, y belongs to S, ixy. You'll see where I'm going in a minute, correct? Correct? So what is the expectation of this? This is just yeah, tell me. So this is the first term is lesser than equal to, so by linearity of expectation, you will get this equal to summation x belonging to S, summation y not equal to x, y belonging to S, of expected number of ixy plus now we are just summing over x equal to S, and ixy is of course 1 because x equal to y, so just 1, correct? Correct? So what is this quantity equal to? What is the expected value of expected value of e of ixy? This is just summation x belonging to S, summation y belonging to S such that y is not equal to x. Probability that hx, h naught, I forgot to write h naught here, h naught x equal to h naught y. And this probability is over h naught, this is over h naught, correct? Plus size of S, which is just n, correct? So now this is equal to summation x belonging to S, y belonging to S, y is not equal to x. And this is, what is this? 1 by m. This is equal to, roughly equal to n into n minus 1 by m plus n plus n, correct? Correct?
Yes, sir.
So if you take m equal to n, this is equal to n minus 1 plus n is equal to, so taking m is equal to n, correct? So this is less than 2n, correct? So the number of items that and I claim that this quantity is precisely equal to this. Is that true? Why is this true? I mean, if there are ni items in the thing, then the number of then so do you see this equality? Is there anybody who doesn't see this equality? Why does this hold? Tell me. See, IXY is just the probability of one collision. You're counting the number of collisions amongst all the, so this counts the total number of collisions, correct? Correct? And so does this. Ni is Ni squared equal to Ni choose 2 is the number of collisions, or let's say Ni into Ni minus 1 is the number of collisions in Ni one, correct? Which is roughly equal to Ni squared, which is equal to order Ni squared, less than Ni squared, correct? So modular linear terms, this is just Ni squared, correct? Are you with me?
Yes, sir.
So in slot I and summing over all i's, you get the same thing as this, correct? So these are the same things, and we have shown, so this is what we wanted to prove, and we have shown that expected number of this thing is less than 2n, correct? So if you take m is equal to n, and you build a table, and you build a table provisioned for basically root n items at each slot, then you would be done. Do you agree with me?
So can you repeat the last sentence?
So equal to n. And using root n. Let me do it again. So you build up n here, and you build a table of root n in which you are expecting root n basically I'm saying that so here I'm missing one detail, which is so like I said, I waved my hands and said that this should work. We build a table that accommodates ni many things. So details go there, and you build an adjustable table that grows if the number of items is more and shrinks if it's smaller, correct? Then you can do this, correct? Dynamically. Or initially, if you know that there are just n items and so on, then you can also do this. Okay, not to confuse you, just think of it this way, that you have ni items being sent to the ith slot, and you know that ni squared under expectation is order n, correct? Then how would you deal with this situation? Okay, so having supplied the basic idea here, let's go into the nitty-gritty details next time. Correct? Is that okay?
Yes, sir.
Okay. Okay. So
So
let's
what
start.
are what are the portions for quiz on Thursday, sir?
What are the portions for quiz on Thursday? Till binomial heaps.
Okay, there. Okay, there is not.
Fibonacci heaps are not there.
Okay, sorry.
Fibonacci heaps are not there. Binomial heaps are all that. Yeah, till. Correct? Okay.
Oh, yes.
Thanks. Thanks.
Thank you,
Okay.
sir.
Okay. Bye.
So, will this hashing also be in the algorithms book?
It's not in the algorithms book. I will, yeah. So one thing about binomial heaps and Fibonacci heaps, I will put a write-up from Cozen's book in the Moodle page. Correct? And if I don't do it by tonight, please remind me. Correct? I will try to do it just now. And for this one, I will also look for some notes and put them on this thing. Correct?
So
Okay,
what
sir.
was the book you mentioned for heaps?
Cozen's book. I will put so remind me if I forget, but I'll in all likelihood not forget and put the notes just now. Correct?
Thank you,
The
sir.
book
So
is by.
actually, also,
Tell me.
sir, could you spell the name? I couldn't.
Do
Okay.
you see it?
Thank you, sir. Yeah.
Yeah. Okay. Okay. Thanks. Bye.
Thank you, sir.